All right. So we now turn to two tests that we can use to test convergence of some infinite series. Okay, so far we have the geometric series. We know how to do convergence on it. Right? If the ratio is absolute value of the ratio is less than one. We had our telescoping series. We were able to look at those. We then were able to test to the divergence, if a series diverges, at least some of them anyway, by the divergence test, right? If the limit of the underlying sequence doesn't go to zero, then we know it's going to diverge. We were able to test some things with the integral test, and then we had the comparison test. And then in the last section, we talked about dealing with alternating series. But none of those tests help us with series like the three that I have listed here, right? On the one hand, I have the series of k squared over 2 to the k. Now, take away the k squared, if I just had 1 over 2 to the k, that's a geometric series, 1/2 to the k power. But that k squared complicates things. And this would be a very difficult function to talk about the integral of that, right? The integral of x squared over 2 to the x. How in the world do I do that integral? And likewise, this thing looks really complicated. Again, how would you even consider doing an integral of it? Don't know. I know that if I had just this stuff, k over k plus 1, the limit of that stuff goes to 1, so that stuff inside would go to 1. But it's not just that stuff inside, it's also raised to that exponent there. So what's happening there? And then here, remember, a factorial is that k factorial would be k times k minus 1 times k minus 2, so on, all the way down to 3 times 2 times 1. Right? How in the world would I do that with an integral? Yeah. So my integral test, which was one of my big tools, falls apart. And likewise, how do I compare these to something else? Right? So those tests just don't really work, the old test we have. And so that's where we're going to look at something known as the ratio test. Something known as the ratio, and then later on something known as the root test. Okay, so first we're going to introduce the ratio test. The ratio test. We say, let the sum of the AK be an infinite series. Let the sum of the AK be an infinite series. Okay. We then say let R equal to the limit as k goes to infinity of the absolute value of AK plus 1 over AK. It's called the ratio test because we're actually looking at the ratio of the terms. We're actually looking at the ratio of the terms. Okay? So, here's the result. If that ratio as k goes to infinity of the next term divided by the previous term, turns out if that's a number that falls between 0 and 1, then we're able to say that the original sequence converges. We're able to say the original sequence converges. Okay. If, on the other hand, that ratio there, AK plus 1 over AK, happens to be a number greater than 1, then we're able to confidently say our sequence diverges. Okay. If on the other hand, r equals 1, our test doesn't tell us anything. It's inconclusive. It's inconclusive. So here's the idea. Here's the idea. We're actually going to, I won't say prove, but basically kind of sketch the proof out. So here's the idea behind the proof. For big K, for very, very big values of K, then if the limit is approaching R, AK plus 1 over K is approximately equal to R. Okay. That means then, since it's approximately the case, then AK plus 1 is approximately AK times R. In other words, this is the recurrence relation definition for a geometric series. For a geometric series. All right, this is a geometric series. And so therefore, being a geometric series, roughly a geometric series for big K, based on this ratio test, are things roughly a geometric series with ratio R. Well, something with ratio R converges if R is between 0 and 1. Of course, with ratio 0, obviously everything just drops off. And if it's anywhere between 0 and 1, by a geometric series, it converges. So that's kind of the rough sketch of the proof. There's more details that kind of need to be put in there. But that's the rough sketch of the idea, is that as K gets really, really big, then pretty much you're right at R, right? If you go far enough over. AK plus 1 over AK is pretty much equal to R. So that means that AK plus 1 is basically AK, the previous term, times R. And that's true for all the terms beyond that point, which makes the stuff beyond that point on the tail of the series, the very end of the series, is approximately geometric. And geometric will converge if R is between 0 and 1. Of course, if R is 0, right, then it would also, of course, converge. Okay? So that is known as the ratio test. That is known as the ratio test. Okay, that's known as the ratio test. And it's a very strong way to check convergence on a lot of series that are very difficult to integrate. But it turns out the ratio test turns out to be pretty good for a lot of them. Pretty good for a lot of them.